Welcome everyone. Today we're going to be evaluating a very interesting infinite series. As you can see, it is a sum of infinitely many fractions, where the numerator is expressed by the function n squared, and the denominator by 2 to the n, where n starts with 1. So let's get right into it. The first step to solving this problem is to test whether or not this series converges. That's not really the main point of this video, so I would just tell you if you simply use the ratio test on this, it will yield a satisfying result that this series does converge. And if you're in a competition setting and don't have time to do that, you can just assume that, and then you can continue with the problem. Once we know it converges, we can assign its value to some variable. And the hope of this is manipulating this variable to yield an expression that will help us. Because right now, this series is not in the form that we can really compute. But one form which we can compute is the geometric series. We all know how to do an infinite geometric series. So if we can get this to some kind of geometric form, then everything should work out nicely and we should be able to find the answer. So that is the general plan. Give it a variable name and try to somehow fiddle around with that variable. So the first step I did in this is to take the half of s and then notice what happens. We can just simply multiply each of these few terms by a half and notice some pattern. So if you take a half s for the first 5 terms in here, you'll get 1/4 plus 4 to the 8 plus 9 over 16 plus 16 over 32 and 25 over 64. Just the numerator goes up, multiplies by 2. The denominator multiplies by 2, and the numerator stays the same. So, that's a good start, but it's not really getting us anywhere to our goal of converting this to a geometric series. But then we can do something else. Let's subtract this 1/2 of s from s, because we can group fractions that have the same denominator. Denominator of 4, denominator of 8, 16, and so on. S minus 1/2 of s will simply be equal to 1/2 of s, but we can look at it now in a slightly different way. And this will yield a result of 1/2 plus 4/4 minus 1/4 here. For the first, I just grouped the fractions with the same denominators. And then for the 8s, we can do much the same. 9 over 8 minus 4 over 8, and so on, like that to infinity. And now we can notice a bit of a pattern here and write 1/2 of an s as a new infinite series and see that it would be a bit more simplified. We can now rewrite this in a new summation notation that should be a bit simpler than the one we had here. It is going to be equal to the sum, is going to equal to 1/2 of s. We'll just write it in our new summation note form right here. And it is going to look precisely like this. N squared minus n minus 1 squared over 2 to the n. And the sum from n equals 1 to infinity. And this is quite simple to notice, right? Because we have right here, as we separate it out by the parentheses, we're subtracting fractions with the same denominator, but their numerators, they are basically the same square, but here there's 1 square and here's the square that is before it, right? 4 and 1, 9 and 4, then there's going to be 16 and 9 difference with it. And this is our new series, and this is very nice now because we can take the difference of squares in the numerator right here. This is going to be the same sum to infinity from n equals 1. The difference of squares, you can apply it and get n plus n minus 1 times n minus n minus 1 over 2 to the n. And this, which is just equal to, right here, that cancels out and we get a 1, is going to be 1 times this, which is equal to 2n minus 1 over 2 to the n. The sum of that. And we have definitely simplified this problem quite a bit now. Instead of having a squared term in the numerator, we have a linear term. And we can now write this out such that there's an odd number in the numerator, and in the denominator, there is that same 2 to the n. But still, we can't really use a geometric series, but we can keep going to make this look like a geometric series. I'm going to erase everything and proceed. So it seemed that our experiment from the start of taking the half of s and then subtracting that half from the whole of s, it allowed us to reduce our square numerator in the sum to a linear numerator in the sum. So that may lead us to believe, if we do the exact same procedure, have s then subtract it from what we have, then we may be able to have a sum where the numerator is a constant, therefore making this whole series geometric and completely doable. So let us do the exact same procedure. We're first going to take the half of s, therefore having 1/4 of s. And let's write out the first couple terms here. It should be quite obvious. We have 1/4 plus 3/8 plus 5/16, 7/32, and 9/64. All right, and then we remove this 1/4 of s from the half of s and get that 1/2 of s minus 1/4 of s. We will do the exact same thing by grouping the fractions with the same denominators. We will get 1/2 plus grouped 3/4 minus 1/4, then grouped again, seems like, 5/8 and 3/8, and so on with all the other fractions. And there really is a very nice pattern here. As you can see, we're subtracting fractions with the same denominator, but their numerators are consecutive odd numbers. So the difference of the numerators will always be 2. And we can rewrite this sum in a more readable way now as this 1/2, which is really the oddball here, plus 2/4 plus 2/8 plus 2/16, and so on. And as our hypothesis was confirmed by doing the exact same procedure of having it and subtracting it, we get a geometric series where the numerator is the same. And we can, of course, rewrite this in summation notation as 1/2, which doesn't really fit in, plus the sum to infinity of n equals 2, I believe, right? It's going to be 2 times 1/2 to the n. And here we have our first term and our common ratio, as is in a geometric series. And we're going from 2 because it seems like here we start with 2/4. Because we don't know how to evaluate a geometric series where the starting n is equal to 2, we can avoid this problem by rewriting this as the same geometric series, instead starting with 0 as we are used to, and then just subtracting the unnecessary terms when n is equal to 0 and when n is equal to 1. So when n is equal to 0, this fraction is 1, we're subtracting 2, and when n is equal to 1, this fraction is 1/2, 2 times 1/2 is 1. So this is equal to 1/2 s minus 1/4 of s, which is indeed 1/4 of s. And now we can just use the formula for the infinite geometric series, which is going to be the first term over 1 minus the common ratio, and then, of course, what we're subtracting as well. And if you evaluate this, you will get that this is 3/2, and this is equal to 1/4 of s, which is 1/2 of s minus 1/4 of s. And finally, we are done, because we now just, to get s, we multiply both sides by 4. 3 times 4 is 12. 12/2 is 6. And this is what this infinite sum from the start we had converges to. What a nice number of 6. Thank you all for watching. Make sure to check out my other video where I evaluate another quite strange infinite series, which is shown right here on screen. And yeah, thank you for watching. I'll see you in the next one.